are good questions, but they become much better when they invite visual thinking. Typically in classrooms, students are expected to draw a table of numbers, then stare at the table until they notice the pattern. The pattern that people may notice is numerical. That is, to find the number of squares in the pattern, you can take one of the case numbers, such as 2, add 1 to the number, making 3, then square the number to get 9. This pattern can be expressed algebraically as n plus 1 squared. The expression that describes the pattern, n plus 1 squared, is a quadratic function. When students work in this way, manipulating numbers and symbols with no connections or meaning, they miss important opportunities to understand mathematical functions. In my work, instead of asking how many numbers are in different cases, I ask, how do you see the pattern growth? Where do you see the extra squares on this shape? These are the questions I asked the CEO that night. I was surprised by his response. It was not that the CEO couldn't see a method of growth, he could, and he described the method to me. He said that he saw the extra squares on top of each column. Other people have described this as a raindrop method, with the squares coming down on top of the shape, like drops of rain coming down from the sky. Figure 1.2 in the enhancement shows this method and other ways people see the growth. But after sharing his method, the CEO asked something I've never been asked before. With genuine confusion in his voice, he asked, "Doesn't everyone see it that way?" I didn't tell him no, I just asked everyone at the table to share how they saw the growth. As we went round the table, everyone shared a different way of seeing the pattern growth. The CEO appeared increasingly flabbergasted, as though it had never occurred to him that there was more than one way of seeing something mathematical. He shook his head in disbelief. We had his attention. Changes to questions to invite a broader version of mathematics are important. When students encounter the narrow, numerical version of a question, and they stare at tables of numbers to see patterns and find algebraic expressions, they may come up with n plus 1 squared, but they have no idea why this expression works or what it means. When we ask students how they see the pattern growth, they understand the function more deeply, and they can understand visually that the shape grows as a square that is always one more than the case number. The last method in figure 1.3 shows this most clearly. This is why we can describe the growth as n plus 1 squared. As dinner progressed, I shared something I'm passionate about, which is rooted in important neuroscientific research. The value of mathematical diversity. The term diversity means difference, variety. In this book, I'll use the term mathematical diversity to include both the value of diversity in people, whether racial, cultural, social, or any other form, and the diverse ways we can see and learn mathematics. I'll also use the term mathish to describe a way of thinking about the mathematics we use in the real world that could be a powerful tool for student thinking. Embracing these concepts of mathematical diversity and of mathish are the keys to stepping into a rich understanding of mathematics that is equitably meaningful for all learners, regardless of education, gender identity, race or ethnicity, and beyond. Research shows that student diversity is key for collaboration, problem-solving, compassion, achievement, and more. But research also shows that when mathematics is embraced as a subject that can be seen and solved differently, it leads to higher achievement and greater motivation and enjoyment. These two aspects of diversity, differences among people and in mathematics, stand alone, but they also come together in beautiful ways, strengthening and supporting each other. If we want to value and encourage all the people we meet who think in different ways, we must reject narrow mathematics, which is the only mathematics most people know.